Namaste, and welcome back to JEE Physics with Typical Monk. This is class 18, Moving Charges and Magnetism. A magnetic field is a curious thing. It pushes on a moving charge, but always sideways, so it steers without ever speeding it up. Set a charge loose in it, and the charge curls into a circle, or spirals into a helix. And every current, in return, weaves a field of its own. Today, we follow the force, the circle, and the field of a loop. One idea at a time. Here is what you will learn today. First, the magnetic force on a charge and on a wire. Second, circular and helical motion and the cyclotron. Third, the Biot-Savart law and Ampere's law, the field of a wire, a loop, and a solenoid. Fourth, the force between parallel currents and the torque on a loop. And fifth, the moving coil galvanometer, plus the drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. The Lorentz force, F equals QV cross B. It is perpendicular to the velocity, and because of that, it does no work at all. Circular motion. A charge moving across a field curls into a circle of radius r equals mv over qb. The Biot-Savart law. Every current element makes a little field, and at the center of a loop, they add up to B equals mu naught I over 2R. And Ampere's law. The line integral of B around a closed loop equals mu naught times the current enclosed by that loop. Now look at the picture. The magnetic field at the center of a current loop. The Biot-Savart law. Each small current element, dl, produces a field dB, and these little fields all add up right around the loop. At the center, the whole loop gives a field B equals mu naught I over 2R, pointing straight along the axis of the loop. The direction: curl the fingers of your right hand along the current, then your thumb points along the field B. A solenoid. Stack many such loops together, and the inside field becomes uniform. B equals mu naught Ni, where N is the number of turns per unit length. Now, the working formulas, the ones the exam turns into marks. The ribbon holds the anchors, the Lorentz force, the radius, and the loop center field. The force on a wire, F equals BIL, sine theta, a current-carrying wire, placed in a field, feels a sideways push. Circular motion, R equals mv over qb, and the period, T equals 2 pi m over qb, is independent of the speed. That is the secret of the cyclotron. Parallel currents. 2 parallel wires attract each other if their currents run the same way and repel if the currents are opposite. Torque on a loop. Torque equals NBI sine theta, and a current loop behaves as a magnetic dipole with a moment m equals NIA. Let us work the G favorite, a radius, a period, and a loop's field. A proton enters a field of 0.5 Tesla, moving perpendicular to it at 2 times 10 to the 6 meters per second. The radius, R equals mv over qb, that is 1.6 times 10 to the minus 27 times 2 times 10 to the 6, all over 1.6 times 10 to the minus 19 times 0.5. Compute. The numerator is 3.2 times 10 to the minus 21. The denominator is 8 times 10 to the minus 20. So R equals 0.04 meters. That is 4 centimeters. The period, T equals 2 pi m over qb, and notice it does not depend on the speed v at all. That is the cyclotron principle. Compute T equals 2 pi times 1.6 times 10 to the minus 27 over 8 times 10 to the minus 20, which is about 1.26 times 10 to the minus 7 seconds. The loop field. For a current of 2 amperes and a radius of 0.1 meters, B equals mu naught I over 2R, which is 4 pi times 10 to the minus 6, about 1.26 times 10 to the minus 5 Tesla at the center. Now what happens when the velocity is not perpendicular to the field? The helical path. A velocity along B. If the charge also moves partly along the field, that parallel component is completely unaffected by the force, and so the path opens out into a helix. The radius. The perpendicular component of the velocity is what sets a circle's radius. R equals m, times the perpendicular velocity over qb. The pitch. The parallel component carries the charge steadily forward, one pitch for every revolution. So the pitch equals the parallel velocity times the period t. The rule. The perpendicular velocity makes it go round in a circle. The parallel velocity makes it advance along the field, and together they trace a helix. Now what JEE actually asks. 5 pointers. 1. The Lorentz force F equals qv cross b, perpendicular to the velocity, so the magnetic force does no work and the speed never changes. 2. Circular motion R equals mv over qb and the period t equals 2 pi m over qb independent of speed, the cyclotron. 3. The Biot-Savart law. The loop center field is mu naught I over 2r. The solenoid field is mu naught n I and the straight wire field is mu naught I over 2 pi d. 4. Parallel currents, same direction attract, opposite repel, and the force per unit length is mu naught I1 I2 over 2 pi d. And 5. The torque on a loop, torque equals NBA sine theta, and the magnetic moment N equals NEA. Now an assertion and reason drill. For each pair are both true, and does the reason explain the assertion? First pair. Assertion: a magnetic force does no work on a moving charge. Reason: the magnetic force is always perpendicular to the velocity of the charge. Both are true, and the reason directly explains the assertion. A perpendicular force can do no work. The answer is A. Second pair. Assertion: the period of a charged particle circling in a magnetic field increases with its speed. Reason: the radius of its circular path is r equals mv over qb. The reason is true, but the assertion is false. The period 2 pi m over qb is independent of speed. A faster particle just makes a bigger circle in the same time. The answer is D. Third pair. Assertion: two parallel wires carrying currents in the same direction attract each other. Reason: a current-carrying wire produces a magnetic field around itself. Both are true, but that the wire makes a field does not on its own explain why the force is attractive, so the reason does not fully explain the assertion. The answer is B. Now match each quantity to its formula. The Lorentz force goes to qv cross b. The radius of the circular path goes to mv over qb. The field at a loop center goes to mass psi over 2I over 2I. And the torque on a loop goes to NBA sine theta. 4 pairs, each worth committing to memory. Now, how many of these 3 statements are correct? 1. A magnetic force does no work on a moving charge. That is correct. 2. The period of circular motion in a field depends on the particle's speed. That is wrong. It is independent of speed. 3. Parallel currents in the same direction attract each other. That is correct. So the answer 2 are correct. Statements 1 and 3. The trap is statement 2. The period 2 pi m over qb is independent of speed. Now the 2 mistakes that quietly cost marks. The myth: the magnetic force can speed up a charged particle. The truth: it is always perpendicular to the velocity, so it does no work. It changes the direction of motion, never the speed. The second myth: a faster particle takes longer to complete a circle in a magnetic field. The truth: the period 2 pi m over qb is independent of speed. A faster particle simply traces out a bigger circle in the very same time. Now, test yourself. Answer in your head before the reveal. That is how G speed is built. Here we go. Question 1. The work done by the magnetic force on a moving charge. 0, always. Question 2. The radius of a charged particle's path. mv over qb. Question 3. The field at the center of a loop. Mu naught I over 2r. Question 4. Parallel currents in the same direction. They attract. And question 5. Does the period depend on the speed? No, it does not. Let us gather it all in one breath. The Lorentz force, F equals qv cross b, does no work. The speed stays constant. Circular motion, R equals mv over qb. The period, 2 pi m over qb, independent of speed. The Biot-Savart law, loop center, mu naught I over 2r, solenoid, mu naught ne. Parallel currents, same direction attract, opposite repel. The torque on a loop, NBI sine theta, the moment, NEI. Next class, magnetism and matter, the bar magnet, and the Earth's magnetic field. A magnetic field steers without ever pushing forward. It bends a moving charge into a circle or a helix, while every current quietly weaves a field of its own. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack JEE. I will see you in the next class.